Okay, let's talk about functions. You've certainly seen functions in algebra, in calculus. We're going to take a more algebraic approach. Functions are very key to what we'll be doing. But the difference, perhaps, between the functions that we do mostly and the functions you've seen before is that we look at functions on finite sets. So we're going to talk about the general notion of function. All right, so here's definition of an ordered pair. You know that you've done this in xy coordinates. The set of ordered pairs from a set is denoted this way. The xy plane can be identified with a set of ordered pairs where each element of which the first number and the second number are both real numbers. And of course, notice that this ordered pair is not a real number itself. So we can define an operation on sets. If you have two sets, any two sets, you can take an ordered pair where the first element in the pair is from the first set, and the second element in the pair is from the second set. And there's some more examples below. For instance, here's one example. These are the numbers on a deck of cards. These are the suits. And any card can be characterized by a number and a suit. You can see that the number of combinations is the number of possibilities for a number times the number of suits. 52 cards. Okay, so you see other examples. All right, other examples that you can do. Okay, so notice that you have an operation on two sets, and you don't create a set, or you don't create a subset of the same set, but you create a different type of element. Okay. In other words, the elements of A cross B are neither elements of A nor of B. Some properties of it's called a set product or cross product, and you can represent the elements in A cross B as a table. Right now, the reason we introduced this product is that we're going to use it to define functions formally. Now, first of all, let's go back to your intuitive understanding of function. Here's a function, f of x equals x cubed. You've seen this in high school or in calculus. You can certainly plot that function. Now the idea of a function is that you have an input x and you have an output x cubed. You could make a table that shows x and x cubed. But for every input x, there's an output x cubed. The set of allowable inputs is called the domain. The set of possible outputs is called the codomain. Now there's a difference between codomain and range. I can say the codomain contains the range. We'll talk more about the distinction lower on. For instance, in this function, x squared, x is always a real number. The output is always a real number. So you could use r as the codomain. However, the output is also a positive real number. So you could use the positive real numbers as the codomain, or non-negative real numbers as the codomain. So the codomain of a function is not unique. Sometimes it might be convenient to choose the codomain of this function, f of x equals x squared, as the real numbers, which is perfectly rigorous and there's no error there. But it's also possible to choose this as your codomain, a set of non-negative real numbers. So the domain is unique, the codomain is not unique. Okay. All right, so this function is not a function from R to R. The reason is it's not defined for x equals 0. You could change the domain. On this domain, it is a function. On the set of all non-zero real numbers, g of x equals 1 over x is a function. All right, so more examples of functions. A table that represents a function, a price function of some food items. Okay. All right, so the codomain of this function would be the set of integers, positive integers. But you could take this set as the codomain, because those are the only prices that are actually attained. So this is the smallest possible codomain, which we call the range. The range is the set of actual outputs of the function. We could represent a function this way in terms of ordered pairs, where the input is the first in the pair and the output is the second in the pair. Or we could represent as a table of values. Okay, so there's some cases where a list is not a function, so you can work through this and see what the necessary conditions are for such a list to represent a function. Okay. All right, in this case, here's another example where this set of ordered pairs does not represent a function, and you can investigate why. Okay. All right, let's continue. All right, so a function can be thought of as a subset of A cross B, because A cross B gives all ordered pairs. A function can be represented as a set of ordered pairs. So a function is a subset of A cross B. However, there are subsets of A cross B that are not functions. And there are additional conditions that must be satisfied by this subset of A cross B. Another way to represent a function is an arrow diagram, and reinforce the idea that each input has only one arrow, has one and only one arrow leading from it. So that's the important. So that's the important condition for a function. For each input, there's a unique output. That's not to say for each output there's a unique input. This 4 has C and D as inputs that produce this output 4. All right, so here's the formal definition of function, which incorporates those two ideas, that f is a subset of A cross B, and for any A in the first set, in the domain set, there's a unique B such that AB is in this set. Okay. So you have domain and codomain. We talked about that before. If you have a particular pair in the function, then B is called the image of A. A is a domain element, B is a codomain element. All right, so we defined a function as a subset of A cross B. So a function is a set of pairs like this. But in order to relate to the usual notation, we also define this notation f of A as the codomain element that's associated with the domain element A. Remember, for each domain element, there's a unique codomain element, and we call that codomain element f of A. As we talked about before, the range is the smallest codomain, so the range is the set of all possible B's that are the second element in one such pair. Okay? We can say that as the range of f is the set of B and B such that there exists an A with f of A equal to B. In other words, there exists an ordered pair in F that has B as the second element. All right, so here's an example. Now remember, the function depends not just on the functional rule, but also on the domain. Okay, so this function is different from a function that was f of x equals x squared, defined, say, on all real numbers. And it's a table representation. You can't define f of 3 because 3 is not in the domain. All right, so other aspects of functions you can read through. I invite you to read through that. So here's an exercise asking you to identify various properties of this function, domain, range, and so on. To draw an arrow diagram, you should know how to draw arrow diagrams. Okay, so here we have more functions, so more examples of functions. Again, these are functions on finite sets, which may be a little unusual for you, but we will be using those quite a bit in the course. All right, so more examples of functions, you have to identify the parts of them. All right, so now we get into various types of functions. One-to-one function. All right, so there's some various examples here. One-to-one, it's easy to characterize one-to-one function in terms of an arrow diagram. One-to-one is also called injective. Okay, so here's an example that shows when functions are one-to-one and not one-to-one. This function is not one-to-one because there's an output with two different inputs. This function is one-to-one because every output has a unique input. This function is not one-to-one because these two inputs go to the same output. So every time you have multiple inputs going to the same output, the function is not one-to-one. It's still a function, it's just not one-to-one. Here's the formal definition. If we have a function from a to b, f is one-to-one. If for all pairs of elements in A, such that f of a1 equals f of a2, then the two must actually be equal. So whenever you have two inputs that give the same output, they must actually be the same element. There's another way of defining this by the contrapositive. Contrapositives can be confusing, but I think in this case it's very useful. Notice that this statement says f of a1 equals f of a2 implies a1 equals a2. So that's really what he's saying here. F of a1 equals f of a2 implies a1 equals a2. Now the contrapositive says that you take the negation of this and that implies the negation of this. So a1 is not equal to a2 implies f of a1 is not equal to f of a2. Okay, so these two are equal. The picture of one-to-one function, I think there was a picture before, but if these are the inputs and these are the outputs, the whole idea is that to every output there's only one input. So I can do this, 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 this. Now there may be some outputs that aren't hit. That's okay as long as there's only one there's only one input for every output. So if I do this, then I've destroyed the one-to-oneness. I have two inputs for one output. Okay, so proving that a function is one-to-one, this is an important exercise, and this is probably harder than the earlier things. Okay, so here's some examples. Okay, so here, if you say, you can say, for instance, if you apply directly to this function f of x equals x plus 1, you suppose that x plus 1 equals y plus 1, and then you use arithmetic to conclude that x equals y. In other words, the outputs are equal implies the input is equal. Okay. Now to show something's not one-to-one, you just need to show an output, to set two outputs equal and show that there are two different inputs that give the same output. So here's two different inputs. G of 1, absolute value of 1 is 1, absolute value of minus 1 is 1. So I have two different inputs, namely 1 and minus 1, that give the same output. Okay, you could draw that picture like this. On your absolute value, you have two inputs, and they give the same output. Now, you probably know from high school math, the horizontal line test, that's kind of the same thing. If you think about the horizontal line test, the outputs are on the y-axis, the inputs are on the x-axis. If I have two inputs that have the same output here and here, that means I have, for the same output, which corresponds to a horizontal line, that line level corresponds to one particular output, I have two inputs. Okay. All right, now notice that the one-to-one depends on the domain. See, before we had absolute value of x was not one-to-one, but if you just choose the natural numbers, then absolute value of x is one-to-one. In fact, for the natural numbers, absolute value of x is equal to x. So if absolute value of x is equal to absolute value of y, that means that x is equal to y. Okay, so here it talks about the horizontal line test. It's the same thing. Okay, so when you have functions that aren't on the real numbers, the horizontal line test is not as useful. Okay, but we point out here that horizontal line test is graphical. It's not really a proof. horizontal line test is a good tool that you can use subsequently to create an algebraic proof. For instance, in this case, if you graph the absolute value, you can see right away it's not one-to-one. It furnishes an example that disproves the one-to-oneness. All right, so let's get through this. Okay. All right, so here's where we get to the contrapositive. Say a function is one-to-one if and only if any element of the range is mapped from only one element of the domain. Function is one-to-one if two different elements of the domain always map to two different elements of the range. So that's what I said before. So this is an alternative definition. You can use that to prove one-to-oneness if you want. Okay. All right, so here's more exercises. All right, so that's one type of function that's useful. Other type of function that's useful is onto, and picture of onto is here. This function is onto. Why is it onto? Because every element in the codomain has an input that maps to it. This function is onto. Every element in the codomain has an input that's mapped to it. This function, not onto. This O in the codomain does not have a function mapped to it. This one here also not onto. Now notice that one is one-to-one, but it's not onto. So the two concepts are not the same. Okay, some examples. Okay. So this is a good question to think about. If the function f is onto, then what is the relation between the range of f and the codomain of f? Okay, so think about that question. That's a good one to ask yourself. All right. So what does what's onto entail? Onto means that every element in the codomain has a input that maps to it. So to show that this function x plus 1 is onto, you need to say, if I choose an arbitrary element of the codomain, call it y, I can find that x, I can construct an x that maps to y. So naturally, if I choose x equals y minus 1, and this is an element in the domain, then f of this x is equal to this y. In other words, if you do the two-column proof, or I can call this f of x, for any element over here, I need to exhibit there is an element over here that, or I shouldn't draw it this way. If I have, for any, again, this is a function so I can graph it. For any element in the range, in the codomain, rather, right, any element y, I need to be able to find an x that maps to it. And this graph looks like this. Y equals x plus 1, so it looks like this. So if I choose this y level, which is this output level, there is a function x that maps to it. This x is y minus 1. This y minus 1 value maps to y. Some other examples, more examples of showing. Basically what you're doing is you're working the function backwards to find an input that gives you the required output. Okay, there may be more than one input that gives you the required output, but you have to show that there's at least one. Okay, now this one is a little more involved. When you have a function that's defined piecewise, it may be more difficult to show one-to-one and onto. All right, so this description suggests the procedure that you should go through. First, do a graph and see that it actually looks like it's one-to-one and on, like it's one-to-one and onto. All right, let's see if that works. Here we have e to the x for x bigger than 0. E to the x looks like this. Then we have 1 minus x squared. That kind of looks like this. If you drew that graph, it looks like it's one-to-one and onto. But to show this, what you need to do is show that for any y in the range, there is an x that maps to that y, and there's only one x that maps to that y. Okay, so if you can show there's a unique x that maps to each y, then the function is one-to-one and onto. And you really have to break that into two cases. If y is bigger than 1, then since the function looks like e to the x, you have to do one alternative, and if y is less than or equal to 1, you'll have to do a different alternative. Okay, so you can follow this through. Okay, so the case for y is equal to 1, what did I say? Equal to 1. I said greater than 1. Y is greater than 1. Okay. The thing is that because the function is broken into two parts, you want to make sure that this part of the function maps in a one-to-one way onto the this part of the function maps x greater than 0 in a one-to-one way onto the y greater than 1, and this function maps x less than 0 in a one-to-one way onto the negative part here, y less than or equal to 1. So these four statements, here's two of them, and here's the other two, characterize the entire statement that the function f is one-to-one and onto. Okay, so here you're supposed to do the same thing. So I suggest to do this, you do the graph first, and then you do try to do similar statements for these two functions. All right, now we've talked about one-to-one and onto. A function's a bijection if it's both one-to-one and onto. That means all inputs have only one output. That's the property of a function. All outputs are the result of only one input. That's one-to-one, and all possible outputs of the codomain are pair. Okay, so these are the three properties here. So some examples of one-to-one onto. Draw arrow diagram of bijection. Arrow diagram of bijection means that basically every point over here goes to exactly one point over here. There's a really exact correspondence between the two sets. To show functions of bijection, you simply have to show that it's one-to-one and then it's onto. So here's some examples for you to inspire you on proofs that will show one-to-one and onto. Okay, so just do some examples here. Okay, so then you get more and more complicated examples. So here you're showing your familiarity with functions, different types of functions, like this domain z cross z. This is the pairs of integers. Okay, you can define a function from the pairs of integers to another pair of integers. Okay. All right, now we get to another important aspect, and I guess I'll leave that for the next video.